So again, today we're going to do worksheet 13, finish it, and then we will start with worksheet 14. So worksheet 13 has to do with inductance, inductors, and energy. So the first concept that's not covered in the book is called mutual inductance. So I want to at least show you how you calculate that. So problem 1 is about mutual inductance, and so I want to give you some time to look at problem 1, read it, and then we will discuss it. So let's do that in about 2 minutes. So let's read just about the the intro paragraph to it, and then we will discuss it. So let us discuss problem 1. So first of all, by definition, this mutual inductance is defined as the following. M12 equals to the flux through the second loop due to the magnetic field in the first object divided by the current from the first object. So I. So let's see how we can figure this out. So here is so for problem 1. So this is worksheet 13, right? So problem 1, you got the current this way, called I1, and you have a loop. This is called I1. You have a loop. The loop has a certain length and width. First of all, the distance from here to here is S, and the distance this way is W, and this way is H, or L, H. This way is H. So loop 1 will produce a magnetic field that goes into loop 2. So we want to find the flux in loop 2 due to the magnetic field of this current. So we want to find the flux. So first of all, the current is up, so the magnetic field comes out, and then it goes in. So the magnetic field here is going in, and the area is facing the magnetic field, so they are both in the same direction. So the flux is simply magnetic field times area. The only thing though, the magnetic field here gets weaker as you go away, right? The magnetic field here is weaker than here, it's weaker than here, it's weaker than here, it's weaker. So it's not the same magnetic field. So what we have to do, we have to slice this thing into an area this way of width. We can call it dx this way, and then the height is h. So we will do this. The flux in object 2 due to object 1 is equal to the integral of the magnetic field from object 1 dotted with the area. So just magnetic field times area because they're in the same direction. Now, let's see. The magnetic field due to object 1, a distance r away. By the way, let me probably poor choice to choose the dx when the integration variable would be r. So I'm going to choose this thing to be dr. And the distance here is r. From here to here is r. Yeah. Magnetic field due to a current carried wire is mu naught times the current in that wire divided by 2 pi r, right? That's the magnetic field part. The dA part is h by dr. The area part is h times dr. Right? This part here is dA. And this part here is the magnetic field. Is B. Now, where are we integrating? From where to where? Well, we're integrating from r equals to what? What's this? From here to here? From S, yep. All the way to here. What is here? How far is this from here? S plus W. Thank you. S plus W. And as you can see, you got mu naught I1 over 2 pi r and h, they all get pulled out. So mu naught h I1 over 2 pi over 2 pi. What remains in the integral is dr over r. What's the integral of 1 over r? ln? Yeah. And when you evaluate the ln of s plus w, and then you do minus ln of s, you end up with just ln of s plus w divided by s, right? That's the total flux. That's the total flux. Do we agree with that? I know I skipped a step with the integration, but I think we did it enough times now that it's okay. Now we can calculate this mutual inductance. Here's what it says. It says simply take your flux and divide it by the current from the first source. So if you divide by the current, what is remaining? Right, divide the flux, just basically cross out the current. What do you have? Yeah. You have everything left except for the current. So it's just mu naught times h over 2 pi, and then natural log s plus w divided by s. That is the mutual inductance. So notice mutual inductance or inductance is much like capacitance. It should be a geometric quantity. It should not depend on the magnetic field. It should not depend on the current or anything. It should just be, you construct the object and it has its mutual inductance. Okay? Depends on the geometry of the object, like width and length and stuff like that. Okay? Make sure it's still going. It is still going. Let's go to the next problem here. Problem 2. So for problem 2, I will not attempt to draw problem 2. It's a ring within a ring. And there is a ring of radius R2 and a ring of radius R1, right? So problem 2. Problem 2. So just for reference, I mean, maybe I will attempt to. Okay. So here is, this is R1. And this is R2. This is the other ring. This is R2, right? And the current in this ring 1, this one, R1, has a current that's going like this, right? This is I1. So, picture you have is better than the one I drew here, but so they wanted to know the mutual inductance ultimately. So we're leading you in the steps. First one says, find the magnetic field due to this ring, due to ring 1, this bigger ring at the center. So what can we say about the magnetic field, B1? Well, it's a ring. We have the formula for a ring at the center of the ring, right? Remember we derived for a ring along the z-axis, there was a formula that depends on z. But here, when you're at the center, how much is z? 0. So it was what? Does anybody have a good memory and remembers that? No. It was mu naught I, in this case we call it I1, over 2R. Yes, over 2R. That's it. That's the, so since it's radius R1, so R1, right? Yep, R1. That's correct. Now, that's the magnetic field. Now what's the flux? You see that, technically speaking, this is for the magnetic field right at the center, right? But if the radius is so big, let me ask you this question. Technically speaking, at the center, is the magnetic field at the center similar to, the same as exactly as the magnetic field here, off center? It's actually not. But they're saying the following. Assume R is so big that when you're near the center, it stays approximately this much. Okay? So we're just using this, saying it's constant. Okay? It's constant. So that makes life easy. If it's constant throughout the area of this ring 2, so what's the flux through ring 2? So what's the flux in ring 2 due to 1? What do you have to do? Ask me. Oh, okay. Any volunteer?
U naught over 2 R1.
Mu naught I1 over 2R1 times what?
1 over I. 1.
So the flux would be what? Magnetic field times what? Area, right? Yeah. So it's the magnetic field times the area of object 2, because it's going through object 2. So the magnetic field is mu naught I1 over 2R1. What's the area of this ring 2? Pi
R2 squared.
pi r, yeah, r2 squared, yeah, so pi, so it is pi r2 to the power 2, and so so this flux therefore is simply, well, that is the flux, okay, that's the flux. To get the mutual inductance, all you have to do is what? Take the flux that you have and divide it by the current, right? And so everything goes away except for, everything remains except for the current. So the current goes away, so you got mu naught times pi times R2 squared over 2 times R1, right? Sure. Mu naught pi R2 squared over 2 R1, yeah, that's correct.
So in the case that the radius of the second was not super small,
Yeah.
the big one, you'd have to integrate it with respect to
Yeah.
power.
Yeah,
Okay.
and that would be a tough integral, because you have to go back to Biot-Savart law and find the magnetic field at each spot as you go away from the center. And that's not going to be easy. I mean, you can set up an integral, but it's not going to be easy. Yeah, I never attempted to do it. Yeah. So if that's okay, we will flip to the next page. So if you go to the next page, it just summarizes, right, of what we just did, right? On page 3. And by the way, it says the mutual inductance on 1 due to 2, M21, instead of M12, they will be equal. Anyways, now we will go to we'll focus our attention now to self-inductance, which is what we focused on in class, right? That's the one the book focuses on. But I didn't want to skip mutual inductance because the book skipped it. Obviously, this is mutual inductance. Is it going to be in the final or no? Yes or no?
Yes.
Oh, okay. I said obviously it's not.
What?
No mutual inductance.
Oh.
Because it's not discussed in the book, so it's only fair to. So no mutual inductance. Not because it's hard, just because it's worth focusing on the self-inductance. So that's the one we'd like to focus on. So now on page 4, it tells you what the self-inductance is. So self-inductance is, instead of having one conductor producing flux through the second conductor, the conductor itself produces flux through itself. So imagine you're a ring, or imagine there is a ring. Here's a ring. If the ring has a current, it will produce a magnetic field. And that magnetic field will go through the ring itself. Right? Through the ring itself, right? A ring produces a magnetic field that will go through itself. So that is flux produced by the ring on itself, and that's why it's called self-inductance. And it looks like this. Instead of saying, instead of calling it 1, 2, we don't need the symbol 1, 2. Just call it one thing without a subscript. And instead of calling it M, the standard name is L. So for self-inductance, it says this: L is equal to the flux divided by the current. Instead of saying flux 1, 2, it's just the flux. Now, if you have one loop, you can say the flux, because there is one flux through one loop. But if you have more than one loop, you will call it the total flux. Total flux. Such as in a solenoid, you will have to multiply the flux through one loop by n, right? Yeah. Sounds good. So that is the inductance. So the question is, the next one is about dimensional analysis. I mean, this one is in henries. The units are henries. 1 Henry is an H, right? So the question is, this one, it says quick check or quick units check. Which of the following statements is or are true? Meaning there may be more than one. So it's the first one, A, says the SI unit for the inductance is the Henry. Is that true?
Yes.
Yes. So because we just said that. Now you have to verify B, C, D, E. Okay? You have to verify B, C, D, E. So for B, it says this. Let me help you with B, and then you do the rest on your own. So for B, it says, let's try to verify. It says 1 Henry is equal to 1 volt times a second per ampere, right? Per ampere. A volt times a second per ampere, right? That's what B is saying. So the question is this true? Is a Henry equal to a volt times second per ampere? Well, we need to look at this, right? Look at this. So first of all, what are the units of current? They're amperes. So if the flux has units of volts times second, then we're good to go. How do I verify that the flux has units of volts times second or not? The easiest, I mean, you can go back to flux, it's a Tesla times square meters, and then go back to what a Tesla is, and it's a mess. Here's the best way to do it, or one way I think about it. I know that to verify this, and by the way, this is true. It turns out it's true. Here's how I verify it. Faraday's law says this: d flux dt, right, is equal to the EMF with a minus sign. But what is the EMF? In what units? Volts. And then so here I have flux, units of flux over time, right? d phi dt. So what are the units of time? Seconds. So the units of flux are actually volts times seconds. Volts times seconds. Yes, so yes. So the D is correct. So now it's your job to do C, D, and E. Let me pause. So let me do this. So it turns out that all of them are true. So let's verify. So we A and B, we verified. C, let's verify C. So starting from here, let's verify C. Okay? Starting from here, let's verify C. So this is true. This is a Henry. Volt times second per ampere. So I got a volt times a second per ampere. What does C say? You got a volt second squared per coulomb. Well, what is an ampere? What's an ampere?
Coulomb per second.
A coulomb per second. So it's a coulomb per second. Second on the bottom jumps to the top, and that makes second squared. So C is correct. Okay. And then let's look at D. Well, again, I will start with well, let's start with this one for D. Let's start with this one. So you got second squared, and you got coulombs. What's a volt? What's a volt? It's a joule per coulomb. Yeah, remember a volt is a joule per coulomb. Yeah, so a volt is a joule per coulomb. So you got coulomb times coulomb is coulomb squared, second squared. So instead of having coulomb squared per second squared, which is an ampere, you have the reverse of that, right? Or the inverse of that. Coulomb squared, second squared per coulomb, which is an ampere squared, but on the bottom. Which is a joule per ampere squared, right? So that verifies D. And then how about E? What is E? E, they say it's an ohm times second. So how can I do the ohm times second thing? What's a volt? V is equal to IR, right? Remember Ohm's law? V equals to IR. So maybe I would start here for that one. So again, there is no set way to start. Just look at the easiest path maybe. So starting with this, so I have my seconds squared, I have my coulombs, but a volt, according to Ampere's law, V equal to IR, so I times R, current times resistance. Current is in amperes, right? Resistance is in, yeah, so maybe, in fact, let me take it back. Let me start here. I should have, that one looks easier. So a volt is an ampere times an ohm, right? V equal to IR, so an ampere times an ohm. So the volt is an ampere times an ohm, and then you got the second left over, and then the ampere from here. So cancel the amperes, and you just get ohm seconds, right? Ohms times second. With checks with the, remember when we were charging that, not charging, trying to run a current in the inductor with a resistor, we had e to the minus L over R or R over L. Let's see. R over L times T. So we mentioned that it was ohm seconds. That's just units, right? Okay. So as you can see, it's a mess. The units can be pretty messy if you try to go back to the original, kilograms and seconds and meters and coulombs. So when you say an ohm, there's so much packed into an ohm, right? There's all kinds of units. I don't know what the combination is. You can go back and verify. Okay. So now let's flip to the next page. We want to learn how to calculate or find the inductors. Okay, let's go to the next page, which is problem 3. You have a solenoid, and I will draw it on the other section. Let me move. All right, so let's look at problem 3. You got a solenoid. We'll put problem 3 here. You got a solenoid that has the current going like this, right? So the magnetic field, in other words, is this way. That's the direction of the magnetic field. Okay. Again, the picture on the worksheet is better than the one I have in here. So the question is, first of all, they're telling me that this coil or this solenoid has radius R, so these loops have radius R, and there is a current I running through it. So I know that the magnetic field is what in a solenoid? Do we remember that? What was it? Mu naught times what? I times n, yeah. So mu naught little n times I, yeah, that's correct. Is it uniform or not uniform? It's uniform, it's constant inside the solenoid, so it's constant. Meaning it doesn't depend on the radius, it's just anywhere on the solenoid, it's the same magnetic field. Therefore, then, the flux, if I want the flux through one loop, what do I do? What's the definition of flux? Magnetic field times what? Area. Right? Magnetic field times area. No integral here, right? Because the magnetic field is uniform. So it will just be the magnetic field, that's the magnetic field, mu naught times little n times I. And what's the area of one loop? Area of one loop? Pi r squared, yeah, pi times r squared. That's the magnetic field through one loop. So what's the magnetic flux through one loop? So what's the flux, the total flux? Flux total. What's the total flux? What can we say about that? If you have n loops. If you have one loop, it's just that. If you have 2 loops, what do you do to this flux? Multiply by 2. So if you have capital N loops, so you will do capital N times the flux through 1 loop, right? Through 1 loop, so you get capital N, mu naught, little n times I times pi times r squared. Do they give me capital N? Yeah, they say capital N, yeah. So, therefore, the inductance, the self-inductance, capital L, what was it? By definition, is what? You take the total flux and divide by the current, right? So everything remains except for the current. The current will go away, and you end up, just divide this by the current, so you got mu naught, capital N, little n, and then the pi and the r squared. That's the inductance of a solid. Yeah.
This bit confused me at the extra n, because when we derived the equation for the magnetic field,
Yeah.
isn't that already taken care of by the little n?
No. So we have 2 things at play. I see what you're saying. So the first n here, this little n, comes from the magnetic field itself. So 1 loop will experience this magnetic field, right? That's how much field goes through it. So 2 loops will have twice this. So if you want all the loops added together, so you have to multiply by an extra n. So there is 1 n that comes from the magnetic field, and there is 1 n that comes from the total number of loops. So in fact, the inductance would be proportional to n squared.
Okay, so little n is just the n.
Little n is little n is comes from the magnetic field. Yeah.
Okay, just one loop.
No, through all of them.
Okay.
From all of them.
What does it represent?
Huh?
What is the little n like? What is
Number
it?
of loops per length.
Ah,
So here's the thing. You make a solenoid, right? Let's say 10,000 loops, and it's 1 meter long, right? 10,000 loops, 1 meter long. So little n is what? Would be 10,000. 10,000 over 1 meter is 10,000. Run a current through it. What happens? You will get a magnetic field inside it, right? How much is that magnetic field? Well, it's mu naught times little n times I, right? Magnetic field is mu naught, little n times I. That's it. That's the magnetic field. Now the question is, what's the flux through 1 single loop? It's the magnetic field, which is mu naught times little n times I times the area of that 1 loop. If I have 2 loops, well, take the same magnetic field, multiplied by the area of the second loop, and add to it the one you did for the previous loop. So add all of them up, that will give you n times the flux through 1 loop. So 1n, the first n comes because you just have a magnetic field. It's a solenoid and it has such a magnetic field. The second one that you're multiplied by is because you're calculating the total flux. By the way, for this one here, is it proportional to capital N or it's proportional to capital N squared?
N squared.
It's n squared, yeah, because this one, although it's written as little n, what is little n in fact?
Big n.
It's big N divided by the length of the solenoid, so it's actually proportional to n squared. And in fact, in class, I may have written it in terms of n squared. Okay. So that's how you calculate the magnetic flux in the solenoid and the inductance of the solenoid. Then we talked also in class about the energy stored in a solenoid, right? So if you flip to the next page, it talks about the energy. So what was the energy in an inductor? I'm asking about the energy, not the energy density. The energy in an inductor is U, and how much is it? Does anybody remember? 1/2
L I squared.
L times I squared. Thank you. That's the energy in an inductor of inductance L. If you want the energy density, this one was what? 1/2 mu naught what? Energy density. Oh wait.
E squared.
B squared, magnetic field squared. This is called energy density. This is energy, it's in joules. This one is in joules. This one is energy density, so what are the units? It's energy per unit of volume, so what are the units of this? Joules per cubic meter, yeah. Joules per cubic meter. So this one is in joules. This one is in joules per cubic meters. Yeah, energy per unit of volume. Okay. Let's look at the next one here. It says, which of the following statements is or are true? Inductors store charge. Yeah? Do inductors store charge? No. An inductor is a perfect conductor. Charges pass through it, but it's not a device to store charges. Capacitors store charge. So the first one is not true. Inductors oppose changes in current. Do they? Or do they not?
Yes.
They do, yes. I mean, why do they oppose changes in current? Because they're inductors. If you change the current, you're trying to change the flux. Faraday's law says there will be an induced magnetic field that opposes the change, and that induced magnetic field produces an opposite flux. So that's what an inductor does. So yes, number B or part B is correct. Choice B. Inductors, they oppose changes in current. An inductor stores energy in the magnetic field. Yes, stores energy in the magnetic field. So yes. How about D? D says a coil wound of N turns has an inductance nearly or linearly proportional to N, to capital N. Is the inductance of an inductor such as a coil, like here a solenoid, proportional to N? No, we just said it's proportional to what?
N squared.
N squared. Yeah. So D is not correct. The work done to establish a current I in an inductor with inductance L is 1/2 Li squared. Yeah. Who does the work to establish that? Well, something has to do it. In the case of a circuit, it would be the battery. So E is correct. So B, C, E are the correct ones. Okay, so we go on to problem 4.